Okay, so the next one says we have a Geiger counter is used to measure the decay of a radioactive sample of bismuth-212 over a period of time. Decays into thallium by emitting an alpha particle according to the following equation, determining the atomic number Z and the mass number A of the thallium nuclei produced, and enter your answers in the spaces below. Okay, well, we know that this alpha particle is really just a 4,2 helium. This is 212. So if that's 212, this needs to be a 208 right here. Thallium. And then if that's 2 and this is 83, seems to me that this needs to be 81. So that wasn't any big deal. Alright, so that was part A. Right there. Then B says, the mass of the alpha particle is 6.64 times 10 to the minus 27 kilograms. Its measured kinetic energy is so many mega electron volts, and its speed is much less than the speed of light. Determine the momentum of the alpha particle. Alright, so I said, well, I know that Ke is equal to 1/2 mv squared. And they told me that it had 6.09 mega electron volts, which is times 10 to the 6 electron volts. And I'm going to change that into joules by saying that there's 1.6 times 10 to the minus 19th joules for every 1 electron volt. So that gave me my Ke in joules, and then that's equal to 1/2. Okay, but I need the mass to be in kilograms, so that's 6.64, 10 to the negative 27 kilograms times B squared. So I solved it, and when I solved it, I got B to be 1.71 times 10 to the 7th meters per second. But that's not, of course, what they're asking me for. They want to know the momentum. So P is equal to mv. B. So P is going to be equal to, well, the mass was 6.64 times 10 to the negative 27 kilograms. The velocity was 1.71 times 10 to the 7th meters per second. So when I multiplied those, I got the momentum to be 1.138 times 10 to the negative, looks like a 19 to me, kilogram meters per second. So that was part B. And again, not a challenge at all. Alright. Part C. Let's see what I can do with part C. Let's see if I can even find it. Okay, that was the first part of B. Okay, so now I needed the second part of B. And the second part of B says determine the kinetic energy of the recoiling thallium nucleus. Well, I have conservation momentum. So the momentum of the alpha particle has to equal the momentum of the thallium particle. So I had 1.138 times 10 to the negative 19th kilogram meters per second is equal to the mass of the thallium particle, and I converted that from U's into kilograms, and I got 3.453 times 10 to the negative 25th kilograms times the velocity of the thallium. So I got the velocity of the thallium to be 3.3 times 10 to the 5th meters per second. But of course that is not what the problem was asking me for. It wanted the kinetic energy. So that's easy. 1/2 m v squared so when I did that, I got the Ke there to be 1.875 times 10 to the negative 14th joules. So that's what they wanted for the second part of B. Yippee skippy. Okay. Now the part C of that question said determine the total energy released during the decay of 1 mole of bismuth-212. Alright, well remember you got to know that Avogadro's number. 1 mole is 6.02 times 10 to the 23rd particles. So if I go back and look at my energy situation, I had 1.875 times 10 to the minus 14th joules of energy for my thallium nucleus. And then I had for my alpha particle, they told me so many, what did they tell me? They told me so many U's. Yeah. So that was, and then I converted those U's, they told me so many mega electron volts, so I converted that to joules, and I got 9.744 times 10 to the minus 13th joules, 9.744 times 10 to the minus 13th joules. So when I added those, I got a total of 9.93 times 10 to the minus 13th joules. And that was the energy that was released from a single particle, but I have 6.02 times 10 to the 23rd of those, because I'm talking about a mole of bismuth. That's the joules for one particle. So when I multiplied those, I found out that my energy was going to be 5.98 times 10 to the 11th joules. Alright, so that took care of that one. The next one was 2001 B7. Let's change ink color and we'll move on. So 2001 B7. Alright, so that one I'm going to pause and write down the equation. Okay, so there's my equation. Now the question says determine the mass effect of a single reaction given the following information. So I was like, okay, well that's not too big of a deal. The mass effect is equal to the mass of the reactants minus the mass of the products. So mass effect, I'm going to call it delta M, the difference between the two. So the mass of the reactants, I have 3 of those. And each of those has a mass, has a, a mass in U's of 2.0141 U. And I got that right from the problem. And then I had an alpha particle, which was 4.0026 U's. I got that from the particle. From the problem, and then I got 1.0078 U's, and then I got 1.0087. So the difference between those, when I did that math, came out to be 0.0232 U's. So there's A. Alright, we got that one handled. B said determine the energy in joules released during a single fusion reaction. So I'm going to convert those used into energy. So I'm going to say that 0.0232 U's. And I know that 1 U is 1.66, 10 to the negative 27th kilograms. And so when I did that, I got my mass to be 3.85 times 10 to the minus 29 kilograms. And then I said, well, that energy is equal to mc squared. So 3.85, 10 to the minus 29 kilograms, times C is 3 times 10 to the 8th. So the energy that was released was 3.47 times 10 to the minus 12th joules. So again, that wasn't any big deal. Alright, then there should be a Part C, and Part C says the United States requires about 10 to the 20th joules per year to meet its energy needs. How many deuterium atoms would be necessary to provide this lovely magnitude of energy? Alright, so that's just a dimensional analysis. So I said that there's 1 times 10 to the 20th joules is my need. I know that every one reaction is going to provide that number that we just found, 3.47 times 10 to the minus 27, minus 12, come on, get it right, minus 12 joules. So I'm going to have to run 2.885 times 10 to the 31st reactions. But I have to remember that every time I run that reaction, it takes 3 atoms of deuterium for every one reaction. How did I know that? I went back to that balanced equation. So it looks like to me I'm going to need 8.66 times 10 to the 31st atoms. All right. And then they wanted us to say what mass of deuterium in kilograms would be needed to provide this much energy per year. So I went and I said, well, let me do a little chemistry there. 8.66 times 10 to the 31st atoms. And that there are 2.01, and actually this is just more dimensional analysis, per atom. How do I know that right there? It was in the problem. And then I know that 1.66 times 10 to the minus 27th kilograms is the same thing as 1 U. So the mass that I need is 290,000 kilograms. All right, I'll post these.